Bismillahirrahmanirrahim. ELE424 Analog Electronics 1 Diode Applications. We are now at the topic rectifiers. There is a slide ELE424 DL Diode Rectifier set2.pdf that should accompany with this video. You should be getting it from your class lecturer. This is video pack 2, video 2, and this is the 5th video in our video pack series. Okay, so the topics that we will cover is half-wave rectification and full-wave rectification. Introduction, what is a rectification? Okay, rectifier is an electrical device which converts AC to DC by allowing current to flow in one direction only. Now, this sounds familiar. So the process of converting the AC, which is the alternating current, into DC current, which is unidirectional, is called rectification. Why convert AC to DC? A DC voltage is required to power essentially every electronic device. So diodes are used in rectifying circuits. Diodes are able to assist rectification because it allows current to flow in one direction only. This is what I meant just now by this sounding familiar, because a rectifier is converting AC to DC in one direction only. And diode is one of the device that you have studied, that is the device that you have studied actually, that allows current to flow in one direction only. So rectification can be achieved by using a single diode or a group of diodes. And these diodes which convert the AC current into DC current, they are called rectifiers. A DC voltage is required to power essentially every electronic device, including personal computers, televisions, and stereo systems. An electrical cord that is plugged into a wall socket and attached to a television, for example, is connected to a rectifier circuit inside the TV. And in addition, battery chargers for portable electronic devices such as cell phones and laptop computers contain rectifier circuits. So it is very important to supply any device with a voltage in the range it is designed for. So the Malaysian electrical system is 240 volts at 50 Hertz. But this diagram I have shown here is from our reference, which is CEDRA. It refers to the US electrical system, which is 120 volts at 60 Hertz. But whatever it is, the concept is still the same. So a diode rectifier forms the first stage of a DC power supply. Okay, you can see it. Maybe I should have it as a laser pointer here. The diode rectifier then converts this sinusoidal wave, for example, to a unipolar output, which can have this pulsating waveform. And then to smoothen the pulsating nature, you pass it through a filter. But this is not covered in our syllabus, but so that you understand where it's being used. So after the filter, there's still some kind of time varying changes there. So the output of the rectifier filter, though much more constant than without the filter, which was pulsating, it still contains time dependent component, and we commonly referred to as ripple. So you pass it through a voltage regulator to reduce the ripple, to stabilize the magnitude of the DC output voltage against variations caused by changes in load current as well. Then a voltage regulator is employed before passing it to the electronic device that you want to supply the DC power with. Okay, so topics in this lecture. We now handle time varying voltages or current signal. Previously, when we covered diode series and parallel connections, all the voltage values were a fixed value. It was a constant. Okay, whether it's a variable or not, but it was not time varying. But now we're looking at time varying voltages such as sinusoidal, and we will look at half-wave rectifier, which means that you know the word rectify in English means putting something right. But here, well, there's nothing wrong with an AC. It's just saying that you wanted to put it in one direction only, and unidirectional instead of alternating direction. So if it is a half-wave rectifier, whatever is in the negative cycle or in the other part of the cycle that we do not want is just omitted. Okay, but if it is a full wave rectifier, it simply means that each part is kept into single direction, but it's not omitted. Instead, it is reflected. It is all made into one direction without omitting any part of the signal. So for the full wave rectifier, we will study two architecture. One is center tapped transformer, and the other one is a bridge rectifier. So half wave rectifier. Okay, and this is half wave rectification concept. When we have a sinusoidal, a full cycle sinusoidal wave, and what we have is just one part, one direction. In this case is the positive cycle, but the negative cycle is omitted. So let's see what happens. The diode conducts only when it is forward biased. That we know. Okay, if the diode is in forward biased, we know. Therefore, only half of the AC cycle passes through the diode to the to the output. So when the input is going through the positive cycle, okay, the flow of current, positive current, is in the direction of the diode positive current flow. So we have this flow here. So this would make this diode to be forward biased, and therefore it will switch on. But if it is in the negative cycle, so Vin, when it is going through the negative cycle, it would then flow in the opposite direction, okay, because it's negative. And this would make the diode to be reverse biased. So when it's in reverse bias, it is essentially an open circuit. So in this case, for our example, for our first example here, we assume a ideal diode, neglecting forward voltage drop at this point. Okay, so when it is going through a positive cycle, it becomes a short circuit. The signal is maintained, but when the diode is reverse biased, it becomes an open circuit, and you omit that part of the signal. Next question is what is effectively the DC voltage? Okay, so because it's still pulsating here, we've not sent it through a filter, but still we can find out what the average DC value is. The process of removing one half the input signal to establish a DC level is called half wave rectification. Okay, we've mentioned that already. I'm just repeating myself. Now Vm here is the maximum applied voltage, which is the amplitude of the input sinusoidal wave. And using ideal diode, the rectified signal maximum voltage, output voltage, is equal to Vm. This was because it was an ideal diode. But if based on the ideal diode model, okay, no voltage drop across the diode, the average DC value is 0.318 Vm. So where do we get this value 0.318 Vm? This comes from the standard known mathematical knowledge, where the average value of a sinusoidal wave, of half a sinusoidal wave, which is based on the net positive area, this positive area above the axis, from one full period. Okay, so from here to here, this would be 0, but this contribution here would be 0.318 Vm. So now later you will see the circuit where the input voltage gives you Vm, but the output voltage will give you something less than Vm. Now when that is the case, when you consider the DC average DC value, you will have to consider 0.318 times the maximum value here, but it's not going to be equal to the Vin if this is going to be less than Vin. We'll see that in due time. So what happens if the diode is not an ideal diode? So you have an average DC value using an approximate silicon diode model. So if it's a diode model, we know that when it turns on, it's not a short circuit, but it turns on to a 0.7 volts. So if you have an input sinusoidal voltage at a maximum value of Vm, what you're gonna get is the output. You're gonna get a maximum value of Vm minus 0.7. Okay, we will see later for our analysis. And also, it doesn't turn on, it doesn't maintain whatever that is less than 0.7. So it's actually, there is actually an offset here. So if it's a T cycle, okay, if it is a T cycle, then where it goes from positive to negative at 0 and T over 2, at 0, the output voltage does not show any signal yet. It's still at 0. and then only after 0, at that point when this input voltage passes 0.7, then only Vout will show any kind of indication of an input signal displayed at the output voltage. So the effect of using silicon diode with VK, well, some of the texts use VK. I should stick to one, right? The previous slide was VF, but VF or VK is the same thing. It's called knee voltage, K and EE. Okay, knee voltage VK 0.7 volt or forward voltage is demonstrated for the forward bias region, and so the applied signal must now be at least 0.7 volts before the diode can turn on. Let's have a calculation of this. Okay, now I'm going to analyze the circuit just now that we had. Okay, just with the hold on. Okay, with the silicon diode forward bias with the resistor R. Okay, we're gonna input the circuit with a sinusoidal voltage signal. Okay, so when the silicon diode VK is 0.7 volts, the diode turns on, and it turns on only when V in is equal or greater than 0.7 volts. So when it is on, VD becomes 0.7 volts, and when we do KVL around this loop, we will get negative V in plus 0.7 because it's turning on, plus V out is equals to 0. So V out is now no longer equals to just V in, but V out is equals to V in minus 0.7. And when it is off, meaning that at any point of this input signal where V in is less than 0.7, it will turn off. It will turn into an open circuit, which means ID is going to be 0. And if I do Ohm's law here to find V out, because all of ID will go through here, if ID is equals to 0, V out, Ohm's law is going to be V equals to IR, since I is 0, so V out is also going to be 0 volts. So if I draw this input to output waveform, so if I have here V in versus time of a sinusoidal wave, where the sinusoidal wave goes from negative to positive value at 0, and the value t, it should be t over 2 here, but let's say this is t and let's say this is 2t. Okay, so what I'm going to have is at 0 it will still be 0. At 0.1, 0.2, 0.3 or V in, it will still be 0 until it reaches 0.7. Then only V out shows V out is equals to V in minus 0.7, and then it will reach a maximum value of Vm minus Vk, which is V in minus 0.7, which we got from KVL. Okay, and then it goes down. Then right after it passes through 0.7, going down again below 0.7, it then becomes V out becomes 0. Okay, which obeys here, because this diode would have turned off when V in is not strong enough, even though it is in the direction of positive current flow. When it is less than 0.7, it will turn off, and therefore you will find this difference between when it crosses positive to negative in V in and at V out. Okay. Alright, so back to the slide. So the maximum rectified voltage is now equal to Vm minus Vk. Okay. And diode turns on and off at input voltage 0.7 volts and not 0 volts, hence the offset on time axis. And if based on the approximate silicon diode model with 0.7 volts, the average DC value now is because Vm is no longer Vm, just Vm equals to V in, but Vm minus Vk. So now the average DC value is VDC is equals to 0.318 times Vm minus Vk. Again, why was it 0.318? That's because that's the average value, average area below a sinusoidal curve, and Vm minus Vk because this is the maximum value of this sinusoidal curve. So this net positive area above the axis from one full period is now reduced because of this 0.7 volts. compared to the ideal model. Alright, now let's do an example with values now. So this is an example 1a. There is another example 1b, but which is just the same, but let's have a look at this first. So the question is, input signal Vin is a sinusoidal 20 volts peak to peak with a period 2t. So by right I should have here, this should be 2t and this would be t. Okay, right, so there's a correction there. So find the DC level and sketch V out versus VT and align it with V in versus T for both cases if the diode is represented by an ideal diode, and then change it to a silicon diode. So first we need to find the DC level, and then we need to sketch V out versus time, align it with V in versus time, and then shift from an ideal diode to a silicon diode. Okay, now let's have a look at the ideal diode. So it's the same thing, the same diagram just now, except that this time there are values. So for the ideal diode, when the diode turns on, V out is equals to V in, okay, from KVL. When it turns off, ID is equals to 0. So Ohm's law says that V out is equals to 0 volts. So at maximum values, when V in is equals to Vm, which is 20 volts, so based on what we've found here, V out is equals to V in, V out is also equals to 20 volts. So this is what we get for V out versus time, aligning it with V in versus time. When V in crosses 0 volts, V out also shows some signal because the diode turns on exactly at that point 0. So both will have maximum value of 20 volts at the peak. Okay, but the negative cycle here has been omitted. So where the negative cycle is, V out is equals to 0 volts, and VDC is 0.318 times Vm, which is 20, and 0.318 times 20 is 6.36 volts. Okay, now what happens if it's a silicon diode? If it is a silicon diode, when it turns on, it becomes 0.7 volts, and it will only turn on when V in is greater than 0.7 volts. So when it is on, VD becomes 0.7 volts. Okay, and if we do KVL here, we have negative V in plus 0.7 plus V out, and so V out is equals to V in minus 0.7. Okay, and when it is off, ID, when it is off, meaning that when you're at the negative cycle or any value below 0.7 volts, okay, when it's a negative cycle here, you can say that this diode turns off. It becomes an open circuit, therefore ID is equals to 0, and if we do Ohm's law, we get V out equals to 0 volts. And if we consider maximum values, at maximum V in is equals to 20. If I look at this from this relationship here, which is V out equals to V in minus 0.7, so if V in is 20, V out is 19.3 volts. So this is the diagram that we have. So when the input signal crosses from negative to positive at 0 volts, at this point V out is still 0 because it's not turned on yet until V in crosses 0.7, then only it turns on. So just after 0 volts, but not exactly, then only it turns on and follows V in, but with a reduction of 0.7 volts. So when V in reaches a maximum of 20 volts, V out reaches a maximum of 19.3 volts. Okay, and then when it goes down, once it crosses 0.7, it then goes to 0 again, and it maintains at 0 until the thing rises again to the negative cycle. So if you can imagine how this plot would look like, okay, if I were to repeat this signal, okay, the input would be sinusoidal, repeats itself, right? But the output will look something like this. Alright, so that's how it repeats itself. Oops. So VDC, sorry, I've scribbled where there's supposed to be some writing here. So the VDC is now no longer 0.318 times 20, but it's now 0.318 times 19.3, which gives me 6.137 volts. So what happens, the student seems to like to ask this question, what happens when you turn the diode the other way around? So the same question, but now the diode is this way. Okay, we've turned it the other way around with the positive terminal connected to the resistor and the negative terminal connected to the positive terminal of Vn. So what's going to happen? Now let's consider the ideal diode first. Okay, for the ideal diode turns on at 0 volts in the negative cycle, because when it's positive, when it's flowing this way, it will be reverse bias, but when it's flowing in the negative cycle, it will be in the positive direction of the diode current flow. So it will turn on below 0 volts. Okay, so when it is on, because this is an ideal diode, Vd is equals to 0 volts, and if I do KVL around this loop, it will be V out equals to Vin. But when it is off, Vd here will be an open circuit, and the concept of open circuit is that ID is going to be 0 volts, and therefore if we do Ohm's law, we get V out is equals to 0 volt. And at the peak value, following this concept here, at the peak value when the diode is on, when Vin is equals to negative 20 volts, it's negative now because it's on in the negative negative cycle, so V out is also going to be negative 20 volts. So this is what's going to happen when the input is a positive cycle. V out is going to be 0 volts, as we said here. But when it is in the negative cycle, it will turn on, and V out will be the same as Vin, reaching negative peak value of negative 20 volts. So if we do a VDC, to get the average DC value, you get 0.318 times negative 20, which is negative 6.36 volts. Now what happens if it is a silicon diode? Okay, the same circuit with the diode connected the other way around, but it is now a silicon diode. It's the same thing, but the diode turns on in a negative cycle only when Vin is less than 0.7 volts. It's actually negative 0.7 volts, if I should correct myself there. This one here should be a negative. Okay, 0.7 volts. Alright, so when it's on, Vd is equals to 0.7 volts, because Vd is already turned connected this way. If I do Kirchhoff voltage law, I get Vin minus V out plus 0.7 equals to 0. So my V out is now Vin plus 0.7 volts, okay, based on KVL. And when it's off, we know that when it's off, it's open circuit. When it's open circuit, the diode current is 0 amps, and when it's 0 amps, I do Ohm's law at the resistor. For V out, I get V out equals to 0 volts. So at the peak value, the negative value is going to be, when Vin is negative 20 volts, V out is going to be negative 20 plus 0.7, which is negative 19.3 volts. So this is how it's going to look like. Anything positive, it's going to turn off, because this diode is going to be reverse biased. But when it is negative, but only when it is less than negative 0.7, only then the output signal will show the pattern of the input signal. Okay, so it's the same thing, but it's on the other way around. So if I calculate the average DC value, it's now no longer going to be 0.318 times positive 19.3, but it's going to be negative 19.3, so it's going to be negative 6.14 volts. And also, if I can comment on how this is going to look like if this signal is going to be repeated. So you have a sine wave that is going positive, negative, positive, negative. So what you're going to have is just positive, negative, then positive, negative. So okay, it's supposed to be the same size, but I'm not a very good artist, but okay, you get what I mean. So next question is, we're still at the half-wave rectifier example of 1A. Now let's compare, because there's a point to comparing this. Okay, bear with me. Compare the average DC voltages if maximum input voltage is not 20 volts but 200 volts, the V in. Okay, the maximum voltage of V in. Now let's see what happens when it is 200 volts. So if Vm of Vn is, the maximum value of Vn is 200 volts instead of 20 volts for the ideal diode, okay, you get 63.6 volts, okay, from 0.318 times Vm. But for the silicon diode, you get 0.38 times 200 minus 0.7, which you get 63.38 volts. So why are we doing this? We want to show that if the bigger the value of V in, the less significant is the effect of 0.7 here. So let's compare this. Just now we calculated for 20 volts, so we got ideal diode to be 6.36 and for silicon diode to be 6.14. So meaning that when you consider the 0.7 volts voltage drop, there is actually a drop of 3.5% of average DC value. But if you're considering an input voltage of 200 volts, that effect of 0.7 volts voltage drop goes from 63.6 to 63.38, which is only 0.35%. So what this value is saying is that the bigger the value of Vm of Vin, the bigger the value of Vin, okay, the less significant is the effect of voltage drop to the average DC level reduction. Okay, so sometimes that's why, even though we know that there is a value for the voltage drop, but because it's not very significant to our calculation, we just assume that it can be an ideal diode. Okay? That is in terms of just practical, having a ballpark average figure when we're doing practical designs. Okay, the next thing that we need to consider is peak inverse voltage. We know that the diode is supposed to go forward biased and then reverse biased as the input signal goes from positive cycle and negative cycle. Remember, in our previous example, there was an issue of breakdown. Okay, because the diode is only forward biased for one half of the AC cycle, it is also reverse biased for one half cycle, another half cycle. So our previous slides touched on the issue of breakdown. So for this slide, when it is supposed to be in reverse bias, it is not supposed to break down, because otherwise it's not omitting that part of the negative cycle that you want to omit or you want to rectify. Okay, so it is important that the reverse breakdown voltage rating of the diode to be high enough to withstand the peak reverse biasing AC voltage. Otherwise, the diode will break down. It is not supposed to break down when it is supposed to be doing rectification jobs. Okay, we do not want the diode to break down when it is rectifying. So there is this such thing as we call peak inverse voltage, or some books call it peak reverse voltage. Okay, and we need to calculate how to find the peak inverse voltage is for our application. So for this example here, okay, that we have here, this, otherwise it would have, we would have this diode, right? Okay, but this diode here, okay, this diode here, when we want to consider peak inverse voltage, okay, when it is going through this reverse part, it's not supposed to conduct. So if we want to calculate the peak inverse voltage, I'm going to erase this. Okay, so we're going to do a KVL here, but how do we indicate what the voltage here is? So the negative terminal, we'll put it as a positive for the PIV, and the positive terminal is negative. So this is the PIV, and I'm going to do a KVL around here. So, oops, it's in the opposite direction, right? So if we do a KVL around here, so we'll get negative Vm plus, okay, plus V out here, sorry, plus V out here. This is going to be 0 volts because this is an open circuit. It's not supposed to break down. We're just looking at it at the limit, at the boundary value. So if this is an open circuit, then therefore this Ohm's law here will say that this V out is going to be equals to 0 volts. Okay. Okay, so minus Vm plus 0 plus P IV, peak inverse voltage, is equals to 0. So peak inverse voltage is going to be equals to Vm. Okay, so whatever architecture you have to consider when it's supposed to break down, and then indicate it with the positive, negative of the peak inverse voltage, do a KVL to find what the value should be. So in this case, the peak inverse voltage should be the maximum value of the input voltage. Okay, we are now done with half wave rectifier. We will now look at full wave rectifier.